Welcome. Today is Thunder Thursday, October 27th, 2022. Today we have a very interesting discussion. Today we discuss the exact physical mechanical difference, between the proton and the antiproton. Now we are given that the proton has a +1 charge and the antiproton has a -1 charge, and that they are mirror images of each other. They are identical. And physicists do not have a clue, what the difference is, other than the charge. That's all they know. They do not understand the mechanical difference. Now, the reason physicists do not understand the mechanical difference between the proton and the antiproton is because they made a false ask-you-me assumption. Oh, yes. Physicists believe that the singularity pulled matter particles and antiparticles miraculously out of vacuum. Okay? That's what they believe. That's what they say. Okay? They strictly follow Einstein's energy equals mass times the square of light, EMC squared. Okay, that's what it says. Okay, and there's a lot of energy, and it is partly true. Okay, it is true that inside the proton permeable sac, and I have discussed that issue before, but proceed for now as if the proton has a permeable sac, okay? And inside the sac are compressed GP1s, okay? That's another thing physicists do not know. They do not know how both mass and energy are stored inside the proton envelope, okay? And also the antiproton envelope, okay? They do not know that neutrons are minted inside the center of stars, and that the neutronium of a neutron star is embryonic neutrons that were degenerated, compressed from hydrogen atoms. So there are two sources for the neutronium in a neutron star. The neutronium is embryonic neutrino, embryonic neutrons, okay? At -300 Kelvin, Adoni degrees below absolute zero. This is how we calculate temperatures below absolute zero. Physicists can only calculate temperatures to absolute zero. They cannot tell the difference between 10 degrees below absolute zero or 100 trillion degrees, okay? What my postulate is based on, it's based on the Siemens refrigeration process. And what that does is you compress a gas to a lower volume. The container heats up, then you extract some of the heat, then you decompress it, and then it will cool to a lower temperature. You do it again and again and again, and you can make liquid hydrogen or liquid helium. Okay? Liquid hydrogen is at 20 degrees Kelvin. Okay, now if you let that decompress, that liquid hydrogen, you can end up with solid hydrogen, okay, at 14 degrees Kelvin, okay? So, but the whole process to get gaseous hydrogen at 68 degrees to a solid at 14 degrees Kelvin involves compression, decompression, heat exchanger. You have to keep removing heat. Okay? Now Earth density is at 5.5 grams per cubic centimeter. Okay? So water is 1 gram per cubic centimeter. And when you average the Earth's crust, the rocks, and the water and everything, you end up with an average density of 5.5 times the density of water. Okay, that's the density on Earth. Okay, now when you go to neutronium in a neutron star, that neutronium is 100 trillion times more dense than Earth material. Okay, if you had neutronium the size of Earth, okay, if you had neutronium the size of Earth, then there would be 100 trillion Earth masses in that neutronium. But that neutronium is not the same type of mass. It's a different type of mass because it's 100 trillion times more dense. Like diamond is carbon, but diamond is different because it's compressed. So what my postulate is that the only way you can get matter in a neutronium star, in a neutron star, to get matter to the density of the neutronium ball of a neutron star is to compress it and then have a heat exchanger. Now, the Earth is doing that. The Earth pulsates every 26 seconds. Our sun pulsates every 5 minutes and 34 seconds, okay? We are given those factors. So there's a compression cycle in the sun, probably for half the 5 minutes, for 2.5 minutes. And then there's a decompression cycle. Okay, that decompression cycle continually removes heat from the center of our sun. Okay, heat is being extracted and a white dwarf is being formed. Now, the white dwarf remnant that will be left by our sun in 7 billion years after its red giant phase, okay, that white dwarf remnant, okay, is only going to be 200,000 times more dense than Earth material. So I multiply by a factor of C of 3 and say that the white dwarf remnant to be left by our sun in 7 billion years after its red giant phase will have an internal temperature of 600,000 Adoni Kelvin degrees below absolute zero. Okay, we can't measure, physicists cannot measure temperatures below absolute zero. Okay, because the absence of electromagnetic waves is absolute zero to physicists. But the only way to get white dwarf matter, the only way to get it to 200,000 times Earth density is to compress and decompress and extract heat. Okay, so our sun has two sources of heat. It has the hydrogen fusion source of heat, and it has this extraction of heat through the 5.5 minute compression decompression cycle. Compression, decompression. So you have compression, heat removal. Okay, so the white dwarf material our sun is going to leave behind in 7 billion years, that white dwarf material will have a density of 200,000 times Earth density. I multiply by 3 and say that the temperature of that material is 600,000 Adoni Kelvin degrees below absolute zero. Now, another interesting discovery lately was that they discovered a white dwarf star that had the size of the moon, okay? And about 50 moons can fit in the Earth, okay? So it was the size of the moon, and it had about twice the mass of the white dwarf that our star is going to leave. So that star being 1/50th the volume of Earth and having twice the mass, it has 1.35 solar masses, and our sun is going to leave a white dwarf of 0.6 solar masses or less. So this white dwarf have 1.35 solar masses, okay? And then a white dwarf becomes a supernova as it approaches 1.41 solar masses. Okay, but the interesting thing is that the white dwarf material in this smaller, more massive white dwarf is 100 times. Okay, so 100 times the density of our sun, white dwarf, at 200,000 times Earth density. Okay, so we move it over and we get 20 million times Earth density. Okay, now 20 million times Earth density still has a lot of heat in it. Okay, because at 20 million times, it's only going to be 60 million degrees, Adoni Kelvin degrees below absolute zero. Okay, so that denser white dwarf, that's the size of the moon, its material, the reason for this is entropy. Okay, so there are two ways to measure temperature. Okay, one way is through the electromagnetic wave spectrum. Okay, so you have a digital thermometer, and you point it to your forehead, and it gives you a reading because of the frequency of the thermal radiation coming off your body. Okay, so thermal radiation from your body translates to a certain frequency and to a certain temperature. Okay, but below absolute zero, we have to go with density. Okay, so gas, liquid hydrogen is 830 times more dense than hydrogen at 68 degrees. 830 times. Okay, now when you get to white dwarf material, our sun's white dwarf is going to be 200,000 times more dense. And then if you double the mass of that white dwarf, then it's going to be 20 million times more dense. Okay, so it's going to be more dense, which means the matter was compressed, and the only way you can compress matter to higher and higher densities to extract heat. So because of the removal of heat is why I say that, and the lower entropy, okay, it has lower entropy, ability to move. Because of those factors, I say that the white dwarf at 1.35 solar masses, about the size of the moon, is at minus 60 million Adoni Kelvin degrees absolute zero. But once you go to the neutronium of a neutron star that has embryonic neutrons, so it doesn't have just the embryonic neutrons that from compressed hydrogen. It also has like neutrino neutrons that were pumped up or minted. So more neutrons are minted than protons and electrons were used to make the neutronium. Okay, and that neutronium in a neutron star is embryonic neutrons. Once you warm up one solar mass of that neutronium, once you warm it back up from 300 trillion Adoni Kelvin degrees below absolute zero, you may have 18 solar masses of neutronium that will decay to hydrogen. That's how protons are made. Now I have to continue this discussion later. Thank you so much for watching. Please like if you like and subscribe to my channel. You can expect more of these entertaining, informative videos every day. Gonna get a new one every day. That's my goal, okay? Plus to lose some weight. Thank you so much. And I appreciate you watching. Bye.